This is lesson 20 of our no-nonsense A-level physics lesson series, and we're going to continue looking at wave properties. So the most important property with regards to waves is called superposition. Let's just make, let's get the pen right, that's a good start, is superposition. Superposition. How do I spell it? T-I-O-N at the end. Which is a fancy way of saying we're going to add up some vectors. So this is the resultant wave that you get when two or more waves happen to be in the same location. This is something that matter can't do. Matter can't superposition, at least not at this level. But waves can. Waves can occupy the same space at the same time, and we add up the effects of those waves. In fact, the word superposition refers to any time we add up the effects of anything. So the vector addition to find a resultant is an example of superposition. But we're going to use the waves as the context to learn about superposition. So let's say superposition is adding together the effect of two or more waves. And that is what we mean by it. So let's give you an example. Let's have an example that we can sometimes call reinforcement. Sometimes we call it that. I'm not a fan of the word reinforcement, actually. Forcement. I prefer to call it constructive interference. And the term interference and the term superposition, they kind of mean the same thing. Interference is what you call it when waves happen to be in the same place and we add up the effects of those waves. Superposition is a more general term, so I guess wave interference is an example of superposition. So reinforcement or constructive interference. There we go. And what would we have in that situation? Well, let's change colour of pen for a second. Let us suppose that I have a wave that is doing this, a nice sine wave, and I add it to another wave that is doing exactly the same thing at exactly the same time. Let us suppose that I'm adding these two waves together. Then what do I get? Well, I'm going to get a wave now where the two influences are combined. And what are these influences? Well, in the y-axis of these little doodles I've drawn, it's displacement, and displacement is a vector. And so I'm not just being displaced by one of the waves, I'm also being displaced by the other wave. So we have the superposition, the vector sum of those two waves' displacement. So we're going to end up with, in this case, if the two waves are identical, twice as much as we had last time. And sometimes you'll hear weird terms like supercrest and supertrough for the superposition. I'm not a fan of those terms, but I'll write them in here anyway. Supercrest and supertrough. It doesn't look like I've written the word super, but I have. Trough. And so all we are doing is adding together the displacements at each instant in time. And I'm going to make a note of that. At each instant in time, we add together seem to freeze up a little bit there. Add together the displacements of each wave. Now, in this case, in the case of superposition that causes reinforcement, in the case of superposition that causes constructive interference, whenever we have positive displacement for one of the waves, we have positive displacement for the other. And so adding those displacements together increases the magnitude of the displacement. And whenever we have negative displacement for one wave, we have negative displacement for the other. And so in that situation, we continue to increase the magnitude of the resultant wave, of the superposition, because they're in the same direction. The displacements are in the same direction. So maybe I should make a note of that. I should say, if displacements, I'll try and write faster, but I'm not a very quick writer, are in the same direction, their addition, we're adding them together, their addition increases the magnitude of the resultant displacement. There we go. And I think that's pretty clear. I think that's okay. So we're talking about displacements here, but of course we could be talking about electric field strength if we're talking about electromagnetic waves, for example, or we could be talking about something else a little bit more esoteric, maybe even probabilities. We don't need to go into that. We can use the context of displacement, that is to say these are mechanical waves, as a nice way in to understand what superposition is. Now, the alternative to reinforcement is cancellation. Again, it's a term I'm not a fan of. I prefer the term destructive interference. But let's just cancellation. How many L's in cancellation? Yes, it is 2. Cancellation. I prefer to call it destructive. That is such bad handwriting. We need to do that again. Destructive, that's better, interference. Okay, so what is destructive interference? Well, let's use a diagram again. This time we're going to have the first wave that we're adding. Let's put both waves so we can see them both on the screen. We're going to have the first wave that we're adding doing the same thing as we had before. So it kind of went up over there, then it went down to there, then it went back to there. And we're going to add this to one which is completely out of phase. It's in anti-phase. Or you could say the phase difference between the two is 180 degrees. Okay? Just like that. And what do we get? Well, we get a resultant displacement at every instant in every position in space at this instant in time of 0. So it's still true what we said before. Each instant in time we add together the displacements of each wave. That's still true. But now what we can say is that the displacements are always in opposite directions. Looks something like directions. So magnitude of resultant displacement is lower. So let's say their addition decreases. The addition of the two waves, their addition decreases the magnitude of the resultant displacement. Okay, there we go. And that's kind of it. Now, what that is going to do is mean that the phase difference between these waves, which at the moment in the first example is 0 degrees, and the second example is 180 degrees, that's going to depend on the time. So what we could say is we could say that the phase of this one, let's say phase of wave A, is equal to, let's say, 0 degrees. And we could say the phase of wave B is equal to 0 degrees. And so the phase difference between them, phase difference between A and B, is equal to 0 degrees. They're in phase. But in this example, the phase of wave A is 0 degrees. But look, wave B is exactly an antiphase. So we say the phase of wave B is actually 180 degrees, or pi radians. And so in this case, the phase difference between those two is 180 degrees. So they're in antiphase. I keep saying the word, I should probably put it in my notes. Antiphase. And these are described as being in phase. Just like that. Okay. But if these are both waves, that means they are moving through time. And we are looking at pictures at an instant in time. Have I made that clear in my notes? At each instant in time. It is there in the notes, but whether or not it's clear enough, I'm not sure. At each instant in time, this is what we are looking at. Space on the x-axis, displacement on the y-axis. I'm pausing here because I'm wondering whether I should add that detail in. Now, I'll leave it like this. It's not overcomplicate it. When you're in antiphase, then there is an instant in time where the displacement is 0 everywhere. It drops to 0. Now, how can I get two waves to interfere? How can I get two waves to superposition? Well, one way is to have the waves travelling in some medium where they're travelling, let's say, towards each other. There's some examples. You can talk about waves on a rope. You can talk about ripple tanks where you've got two sources of vibrations at the top of the water. Sound, you could have two speakers in a room. There's lots of examples where you can have two waves. But let's just take that, any of them. Let's say two waves. That is terrible handwriting. My apologies. Two waves, and let's say they are superpositioning. So these two waves, whatever they are, electromagnetic waves, mechanical waves, it doesn't matter, they are going to superposition. And they're going to do that by travelling in opposite directions. So maybe we're going to have wave A, which is doing this. This is what wave A is doing at some instant in time, but it's moving in this direction. So this would be the velocity of wave A. And then let's suppose we've got a second situation where we've got wave B, and I'll draw it like this. Let's do it like this. So it's the same sort of wave, same amplitude, same frequency, at least I'm trying to. And that is going to be going in this direction, and that's going to be UB, and that's going to be wave B. So these two waves are going to superposition. And what you're going to see is there will be instances in time when all the peaks line up and all the troughs line up. But there'll be other instances in time where all the peaks line up with all the troughs. The peaks from one wave, from wave A, line up with the troughs from wave B. So if we just watch what's happening with the peaks and troughs, we can see that there will be at one instant, well, actually more than one instant, but let's say at one instant in time. Come on. Handwriting is all over the place today. This is a bad day. One instant in time, we can say all crests from A align, they coincide, they're incident with the crests, come on pen, with crests from B. But at another instant in time, let's say a different instant in time, scrolling all over the place, come on pen, all crests from A align with troughs, spell it right, troughs from B. Now, that means at one instant in time, we're going to get constructive interference. And another instant in time, there's going to be destructive interference. And we're going to cycle between the two. And that's the way it's going to work. And because the waves are moving, at one instant in time, if we look at a particular point in space, it will be a crest for A coinciding with a crest from B. But then, about half a time period later, that will then be a trough from A, but also a trough from B. Remember that A is moving at a certain velocity, and it has a certain frequency. And if A and B have the same frequency, and they have the same wavelength, they're traveling with the same speed. And if they're traveling at the same speed, but in opposite directions, that means the distance that one full wave of A takes in one time period is one wavelength. And the distance that one full wave of B travels in one time period is one wavelength, but they're in opposite directions. It's really hard to get your head around this, but it's worth trying. So when there's a peak from A lined up with a peak from B, a crest from A lined up with a crest from B, half a time period later, that same place in space where there was a crest from A, there's now a trough from A, because A has moved to the right half a wavelength. And there's also a trough from B, because B will have moved to the left half a wavelength. I'm not going to write those words down, it'll take me hours to do so. But what that means is that you are going to see the superposition of these. At some points in space, the displacement becomes really high, a super crest, and then half a time period later, where there was a super crest, there becomes a super trough, and it will oscillate between them. But, interestingly, there are other points in space, exactly halfway between those interesting places where you get super troughs and super crests, exactly halfway between them, we'll have places where the displacement from A is always in the opposite direction to the displacement of B. It's just the way it works. Now, I can run various lovely simulations to show you this. I don't really want to, because I want this to be no nonsense. So what we are describing is a stationary wave. So a stationary wave is the situation we've got here. This forms a stationary, come on, wave has a W in it, a stationary wave. And next lesson we'll be talking much more about stationary waves and how they work and how superposition works for stationary waves. We'll be talking about nodes, might as well bring it in here, nodes, which are where crests of A align with troughs of B, and we've got things called antinodes, which are exactly the opposite. These are where crests of A align with crests of B. And two waves are moving, and so what we see is like a skipping rope being swung around, where at each end there might be no displacement ever, therefore the amplitude is 0 because the maximum displacement is 0. But in the middle, the maximum displacement is very high, and so the amplitude is very high. And somewhere between those, you end up with smaller amplitudes. Now, I don't want to go into that now because we'll do that next lesson. So let's just pause that and look at another example of superposition. And again, this is going to come up in a later part of the course as well, when we look at diffraction a lot more. Superposition is the reason for diffraction, but this is an example in which we use a ripple tank. We talked about a ripple tank before. And in our ripple tank, we might be able to see if I have two sources of waves, one here and one here. Let's label them source. I've used A and B. Should we call it source 1 and source 2? I've been using A and B all day. There we go. Then we can have a look at what happens. So at some instant in time, we will see that there are wavefronts like this, positioned one wavelength away from those sources. And then another instant in time, the wavefronts will have moved one wavelength, and the wavefronts for the source 2 will have moved one wavelength, and so we'll see that. And then another instant, each of these is one time period apart, we will see another set of wavefronts doing this. And then another time period later, we would see, try and do it like this, and try to do it like this, down to about there-ish, and so on and so on. And so as these waves propagate, what do we see? Well, we see certain points, I'll colour them in red, where the waves agree. Remember, these lines represent wavefronts, and we could decide that these wavefronts are where we have where we have a what do you call it? A crest. So these are various crests that I've drawn there. And what do you see? Well, all the crests seem to line up along that line, but they also seem to line up along that line, and they also will seem to, if I do a better diagram, they line up along this line, and so on. So you'll see those sorts of things. We can say that these would be where the amplitude is highest. Amplitude higher. Because of superposition, we're adding those amplitudes together. But we also have interesting points like this one here, and this one here. And we've got other points like this one here, and this one here. Now what I'm doing with these dots is I'm drawing points where we have a crest from one of the waves, from source 2 or 1, and a trough, in other words, exactly halfway between the crests, for the other one, source 1 or 2. So you end up with various lines, and you can see there's one there, and there'll be one there, and there'll be one there. Various lines that go between the red lines where the amplitude is lower. Amplitude lower. In fact, you'll even have amplitude of 0 in some places, but let's just say lower for now, because it won't always be perfectly cancelled. So what does that mean? Well, if there's a ripple tank, we're saying there's two sources of waves. There's some positions where the waves have very high amplitude because of the superposition of these waves from these two sources. But there's other places where the wave amplitude is actually very low. So imagine this is a lake, and there's two rivers feeding this lake, and those two rivers cause waves as they enter this lake. If I sail across this lake from bottom to top in this diagram, I'm going to go through regions where there's lots of waves, then regions where there's no waves, then regions where there's lots of waves, then regions where there's no waves, or at least lower waves. And we can test this with microwaves. We could use a microwave emitter and two slits to act as the two sources, and we can get a microwave detector and move it around in this space and see sometimes we get a lot of signal. That's where the red dots and red lines are in this diagram, and sometimes we get very little signal. That's where the green dots, the green lines are on this diagram. I've just realized that my diagram is very badly drawn because I should have a red dot there and a red dot there. And I am actually going to correct this slightly. Let's delete this line there, and let's delete this line there, and let's draw better lines. I've got a straight line tool and everything, and I'm not using it. So that would sort of line up there, and that would line up there, down to there, and so on. So that's slightly better. Now the green ones aren't quite right. It's hard to draw, but that's what you would end up seeing. And I'll stop there. That's all I want to say about superposition, which is all about this wave property. So next lesson, I think it's lesson 21, we're going to be looking at stationary waves and progressive waves, and stationary waves in more detail, nodes and antinodes and different harmonics. We're going to look at that for a couple of lessons, actually, because it's quite a big, complicated topic. So I hope you'll join me then. Thank you very much.